Okay, we have a lot of fun stuff planned today, so let's get into it. I'll go over an announcement. We've been announcing a lot of pre-medical societies before class every day, and so if you prefer to perform medical miracles on quadrupeds instead of bipeds, the PVSA, the Pre-Veterinary Society meeting is happening tonight. Sorry for the late notice, I just got this yesterday. But if you can't go to the meeting, you're interested in the organization, I encourage you to check them out. I am the faculty advisor for that organization, although that's totally a figurehead position, so you won't actually see me at the meetings. But anyway, it's a good organization from what I can tell. With that, we'll get into chemistry. And actually, one other announcement before I start talking about atomic orbitals. There is a tutoring resource available that I want to make sure I advertise because I haven't done that yet. I think they keep changing the name of it, but it's something like the ACS Help Desk or something like that. I don't know. They keep it's basically free tutoring that the American Chemical Society Student Organization offers, and that's going to be Fleming 220 is the room number. So Fleming is sort of right across the street from here. It's on the second floor of that building, and they're typically available. I think it's like 10 a.m. to 6 p.m. or maybe even longer than that. They probably have the hours posted on the door if you ever go there. So it's available every day. It's walk-in tutoring. You don't have to pay for it. You don't have to schedule an appointment. And the students that are in there are undergraduate students who had previously taken these courses and did very well in that. I think they're required to get an A in the course to be able to be a tutor. So there is some selection process that goes into this, so we can vouch for the tutors being very good students who are typically also good tutors. So that, and I encourage you to go to that as a source of extra help if you need it. So that's when everyone to keep that in mind. Okay, so today we're going to move on to talking about atomic orbitals, a bit more of an advanced theory of atomic structure than what we did last time. So last time we talked about the Bohr model, which was the idea that in a hydrogen atom you have the nucleus, you have the electron orbiting around the nucleus in these regular fixed circular orbits. And it allowed us to predict the energy levels quite accurately, and allowed us to predict absorption and emission of photons very accurately as well. But there are some problems with the Bohr model, and the big one that we already talked about is that it doesn't work for multi-electron atoms. So everything you want to know about hydrogen, or not everything you want to know, but a lot of things that you want to know about hydrogen can be predicted from the Bohr model. But if you go to anything more complicated than hydrogen, it breaks down. So if we try to use the Bohr model on multi-electron atoms, we find that it doesn't accurately predict their energy levels. So if we observe the photons that are emitted when we excite multi-electron atoms, and we try to use the Bohr model to predict where those wavelengths will be, it just doesn't work at all. So it's an insufficient model to say anything about multi-electron atoms. So as always happens in science, they needed a better model. And the first thing that people tried was to model in elliptical orbits instead of circular orbits. So the Bohr model says that the electron's going in a perfect circle around the nucleus, and then the first thing people thought about was, well, what if it's not actually a circular orbit? What if it's elliptical, an elongated sort of orbit? So they tried to adapt the model to include this, so it would obviously be mathematically more complicated because it's not a fixed radius anymore. But the long story short is that this didn't work either. So this was kind of their first pass at modifying the Bohr model. And that this was also ended up being a failure. Alright, so this didn't lead to any improvements in the Bohr model when you tried to apply it to multi-electron systems. Alright, so the reality of the situation, which I already gave you this first part last time, the Bohr model only predicts energy levels for one electron system, so don't try to use it otherwise. As it turns out, we're not going to have a simple model for predicting energy levels in multi-electron systems because it becomes mathematically very complicated very quickly, even with only two electrons. But if you're going to use the Bohr model, it has to be for a one electron system, nothing else. So the only neutral element this works for is hydrogen. We saw that there's some ions that you could formulate helium plus, lithium 2 plus. As long as they have one electron, you can still use the Bohr model. But it doesn't work for anything that has more than one electron. And the other reality of the situation is that even though the Bohr model gives us quantitative reproduction of energy levels and photons that are absorbed and emitted, it's not actually a realistic model in terms of a physical model. So electrons don't actually move in circular orbits. All right, it's a nice picture to think about, and a very simple and satisfying one, but it's just simply not true. We don't have, even in hydrogen, where the Bohr model works, you don't have very simple circular orbits. So that was kind of an earlier, more primitive model of the atom. Turns out that physical reality is not true, even if some of the predictions made by the model fit quite well. So we needed a more in-depth, a better model for electrons and atoms and where they're located and their energy levels, and that's where the Schrodinger equation comes in. Now, this is mathematically very complicated, so we're not going to give you all the mathematical details of this, nor are we going to expect you to understand this in any great level of detail. But we do want you to know what it is, what it looks like, and what some of the features of it are. So what it looks like is H psi, so another Greek letter to learn is psi, looks like a pitchfork, and that equals E psi. Now this looks a little bit strange, because well, wait a minute, doesn't that just mean H equals E? Well, H with a little caret above it is not a quantity, it's an operator. And what that means is that it's a set of mathematical functions that you apply to another mathematical function. So like I said, if you were to write out the full mathematical form of H and the full mathematical form of psi, it would look borderline ridiculous, and it would require some knowledge at least at the probably calculus 2 or calculus 3 level, which is not a prerequisite for this course, so we're not going to go into it. But in terms of just a broad level definition of everything, H with the hat above it, as we said, is an operator, and it's called the Hamiltonian. So it's representing a series of mathematical operations and we're carrying out those operations on what we call psi. I'll give you the definition for psi here in a minute. So basically psi is another mathematical function. You apply a bunch of mathematical operations to a mathematical function, and in doing so you extract one of the allowed energy states, which we call eigenvalues, but I don't think that terminology will come up in this course. And that's what E represents as one of the energy levels of the system. And then this other part, psi, is what we call a wave function. All right, and so the key feature of this new model, this quantum mechanical model for the atom that revolves around the Schrodinger equation, is that we no longer treat an electron as a discrete particle moving in a very regular orbit around the atom. We treat it as, we describe the electron as a standing wave. So we've already talked a bit recently about how there's this wave-particle duality, the idea that energy and matter are not really distinguishable from each other, and that particles have wave properties and vice versa. And this is really built into this Schrodinger equation and into this quantum mechanical model, the idea that the electron is in an atom better described as a wave as opposed to as a discrete particle moving in a regular orbit. So it describes the electron as a standing wave. It's parameterized in terms of x, y, and z coordinates, or alternatively in polar coordinates, but we're going to talk about things in terms of regular Cartesian x, y, and z. So it's a function of x, y, and z that is related to, is a wave function for the electron. And what it's related to is it doesn't tell us the exact position of the electron, so that's what it does not tell us. We're going to talk about the significance of psi, this wave function, more as we go through, and that's another key distinction. So because the electron is modeled as a standing wave, we can't know at any given time what the electron's exact position is. All right, so we can't know that from the wave equation, from the wave function. And then the other important key thing to keep in mind here is we talked in the Bohr model about how there's these different energy levels in the hydrogen atom. N equals 1 is the one that's closest to the nucleus and has the lowest energy, and then N equals 2, N equals 3, N equals 4. And so each of those energy levels is going to have its own wave function associated with it. So when you have different energy levels in an atom, which we will always have and we'll talk about in more detail as we go through, each energy level is going to have its own wave function that describes that energy level. And there will be some key distinctions between those wave functions that we're going to get into as well. So that's the Schrodinger equation. We don't want you to understand it in really great depth. If you ever take physical chemistry in the future, that's what you'll learn all about there. But for now, we just want a base level definition and understanding. Now, the other important part of this is what's called Heisenberg uncertainty principle. So this is very much related to the Schrodinger equation. It's a little bit more general. It can apply to particles in many different situations. It's not specific to electrons around atoms, but it's another key point. And then so the equation that dictates the Heisenberg uncertainty looks like this. We're not going to actually use this equation in problems. We're just going to talk about it. Okay, so it's delta x times delta mass times velocity is greater than or equal to h over 4 pi. So delta x is the uncertainty in position. And so in other words, this is how certain can we know what the position of a particle is. The Bohr model gave us a very clear picture of the position of an electron. It said, well, it's in a circular orbit at exactly this radius. We know now that's not true, so then in reality, what is the level to which we can know the position of something? That's delta x. M is whatever the mass of the particle is. We know for electrons that's a very small number. And then delta v, sometimes abbreviated as delta u, is the uncertainty in speed. So it depends on how fast the particle is moving. So what this Heisenberg uncertainty principle tells us, and why then the Schrodinger equation and the quantum mechanical description of the electron are important, is that it tells us that it is impossible to simultaneously know the position and velocity of a particle. Or I guess more accurately, the position and momentum, because that product of mass times velocity is the momentum if you're taking physics. And like most of these ideas that we've been introducing in the context of wave-particle duality and quantum mechanics, it really only matters for very small particles. We're going to see an example on the next slide that demonstrates that. So once again, going back to the example I gave for the de Broglie wavelength, where I said if I were to chuck a baseball to the back of the room, what's the effective wavelength of that baseball as it moves through space, and it's exceedingly tiny compared to the size of the object. And same is true for Heisenberg uncertainty principle. If I throw the baseball to the back of the room, we can measure its velocity with some amount of certainty, and also at the very same time we can measure its position. And compared to the size of the baseball, the uncertainty in the position is very tiny. So for large objects, we can, with pretty good certainty, know where their position is, what their momentum is at the same time. But when you're talking about things that are really small, like electrons, you have this limitation in how certain you can be about their position and momentum. And so that's the key point, is that this really only matters for very small objects. It's not something that you're going to encounter in everyday life, but when we're talking about atoms and looking at the microscopic level, it can be an important consideration. Okay. So that's the deal with the Heisenberg uncertainty principle. And like I said, we're not going to do these types of calculations on homework assignments, but let's do one for fun to see how this manifests itself. Okay, so if we have an electron moving at a speed of 1.0 plus and minus 0.1 times 10 to the 6 meters per second. So remember, for measured quantities, you have uncertainty in those measurements. So this would mean that the electron is moving somewhere between 0.9 times 10 to the 6th and 1.1 times 10 to the 6th. There's an uncertainty of 0.1 in that last decimal place, that last significant figure. So if that's the speed of the electron, and what is the uncertainty in the position? In other words, if the electron's moving that fast, how certain can we be about where that electron is at any given time? and that's what the Heisenberg uncertainty principle allows us to calculate. And this, it's really not possible to know the exact speed of an electron in an atom, but this is a reasonable, it's a large number, but it's a reasonable speed for an electron if you're, for example, shooting one through space in a cathode ray experiment. Okay, so that's the numbers that were given, so we're going to use Heisenberg uncertainty principle to figure out what the uncertainty is in the position. So we're going to write it like this. Remember, it has to be greater than or equal to h over 4 pi. H is still Planck's constant, that same h that we've been dealing with a lot lately. And we need, and the delta v is given to us. The uncertainty in the velocity is that plus and minus here. So it's plus and minus 0.1 times 10 to the 6th meters per second, written in more standard form as plus and minus 1 times 10 to the 5th meters per second. So that's the uncertainty in the velocity. I'm just telling you that's what it is. If you were measuring this experimentally, that's what you'd come up with by doing a number of replications and knowing the precision of your instrument, all that stuff you'll talk about in lab. So that's the uncertainty, and we want to calculate delta x. We rearrange the inequality. We know that delta x has to be larger than h over 4 pi m delta v. So we just move the m delta v over and rearrange. And so then we plug the numbers in. H is still Planck's constant, 6.626 times 10 to the minus 34. 4 pi. And then the mass of the electron I'm giving you here, we talked about it earlier. It needs to be in kilograms for this because we're using SI units. Grams is not the SI unit for mass. And then the uncertainty in the velocity is 1 times 10 to the 5th. Okay? And so when we work out the numbers, we get 5.8 times 10 to the minus 10 meters, which, if we want to put that into nanometers, our favorite length unit in this part, is about 0.58 nanometers. Now, that may not sound like a very large number. You're like, oh, well, that's a tiny uncertainty, so why, does Heisenberg uncertainty even matter? But keep in mind that this number here, 0.58 nanometers, is 10 times larger than a hydrogen atom. So when we are talking about electrons moving very fast at an atomic scale in a hydrogen atom or any other atom, the uncertainty in the position is going to be very large compared to the size of the atom. So we can't really know where the electron is at any given time. The wave function won't tell us that, and so that's related to Heisenberg uncertainty and has, of course, implications when we talk about wave functions for electrons. All right, so this is all very abstract at the moment and very mathematical. So let's get into some more pictorial representations of wave functions and a little bit simpler definitions, perhaps. And so let's start talking about some of the key terminology we're going to use. An orbital which is what the topic of today's lecture is. If you look at the title slide, an orbital is mainly it's just a synonym for a wave function. And it's probably the term you'll hear more often in chemistry. Now, usually orbitals are given in more of a pictorial sense than a mathematical sense. We're going to work up to that as we go through today. And what an orbital allows us to do, and we consider an orbital, is allows us to determine the probability of finding an electron in a given position. So even though the wave function or the orbital doesn't tell us exactly where the electron is around the atom, it gives us a probabilistic picture of where the electron is going to be located. So the orbital allows us to determine the probability of finding an electron at a given position. And there are two ways of defining that probability that we're going to talk about. The first one, which is probably not as useful but is still important to understand, is what's called probability density. And this is simply given by psi squared. So it's still a mathematical function, but you square the wave function, and that gives you a function in terms of x, y, and z that tell you the probability of finding the electron at any point x, y, and z relative to the nucleus. So it's the probability of finding an electron at a point in space. And for psi squared, you're talking about if we just zoom in on one specific point that we're interested in. What is the probability of finding the electron there? Or the relative probability, I suppose. So that's what psi squared tells us. The more useful parameter, the one that allows us to then draw pictures of orbitals that are a little bit more satisfying graphically and that allow us to understand things a little more intuitively, the more important one is radial probability density, and that's given by 4 pi r squared psi squared. So we take that probability density and we multiply it by 4 pi r squared, where r is the distance from the nucleus that we're considering. And this tells us the probability of finding an electron at that certain radius. So if you go so far away from the nucleus, how likely is it that the electron is going to be at that distance from the nucleus? Anywhere in space, anywhere in that sphere that's defined by that distance. Okay, so that's what radial probability density is. A way to think about, radial probability density is, let's say you have an atom, imagine it as like an onion. So an onion, you have these concentric layers that you can peel off one at a time. So the radial probability density would tell you if the atom was, arranged like an onion, what's the probability of finding the electron in one of those shells that you peel off, one of those layers that you peel off. So it's a sphere defined by a certain radius, and what's the probability of finding the electron somewhere within that sphere at that radius? That's what, or I guess at exactly that radius on the surface. So that's what radial probability density tells you. It's a little bit more useful in some cases than probability density. So let's draw graphs of what these look like then. So for the hydrogen atom, the ground state hydrogen atom, that n equals 1 state that we talked about for the Bohr model. So we have probability density on the left. That's just given by psi squared. I'll write that a little bit bigger if you can't see it. So that's psi squared. We're going to do here. The bottom, the x-axis, is given by the radius. So again, we're talking about the distance from the nucleus and what does these different probability densities look like. If you look at probability density of just psi squared, it's just it's a monotonically decreasing function. Which I didn't do a great job of drawing, so I'm going to try the second half again. Okay, so it looks something like that. There's pictures of these in your book that may or may be better. So we see that it decreases with radius. And it's never zero. So it sort of asymptotically approaches the axis but never gets to zero. So that's what psi squared looks like. Now this might seem a little weird to you. You might be thinking, well, if the probability at the nucleus goes to infinity, well, doesn't that mean the electron is most likely to be found at the nucleus? That's not really what it says, because remember, the region around the nucleus is a very tiny region. So if we talk about radial probability density, where we're taking that psi squared and multiplying it by 4 pi r squared, you basically have two functions that you're multiplying together. Psi squared goes down as you go that way, as you go from left to right, and then the 4 pi r squared function continually increases as you get farther away from the nucleus. And so what that leads to in the function for radial probability density is a peak here. So it looks something like this. In other words, the layers of the onion get bigger and bigger as you go out. So even though the absolute probability at one point in space is low for that layer of the onion, it's a very big region of space that you're considering, so the total probability is not going to be as small, and that's why you get this peak here. It still doesn't go to zero, just like the probability density. It never goes quite to zero. And so what you have are some features here. This is what's called the most probable radius. So wherever that peak is located is what's called the most probable radius. It's the radius where you're most likely to find the electron. And the value for hydrogen is 0.529 angstroms. So again, about 10 times smaller than that uncertainty we calculated before. So that's 0.529 times 10 to the minus 10th meters. Very small number. And that's also the radius that's predicted by the Bohr model. So there's some agreement here. The difference is the Bohr model would say that in the ground state, the electron is exactly at 0.529 angstroms away from the nucleus, moving in a circular orbit. The quantum mechanical model says there's a probability of that electron being anywhere, but the most likely probability is that it's at 0.529 angstroms. So the electron could still be much closer to the nucleus than that. It could be farther away from the nucleus than that at any given point in time. We can't really know exactly where it is. That's what the whole idea of this is. Now, the other thing to think about is if the probability never goes to zero, that kind of has some wild implications. So imagine that I had a hydrogen atom here at the front of the room, and it has one electron somewhere around that nucleus. That would mean that there's a non-zero probability of the electron being all the way in the back corner of the room. Now, if you talk about what that probability actually is, it's 0.000000000 whatever, however many zeros, but it's still not zero. So that means in this quantum mechanical model, you never have a zero probability of an electron being found somewhere, but it just gets very, very small as you go farther and farther away from the nucleus. Another key thing that we often define for orbitals, and what we're going to start doing when we start drawing pictures of these, we can shade what's called the 95, or I guess 90% probability region is how your book does it. So if we basically integrate this curve, if you're familiar with calculus, and we find 90% of the total area of this curve, that tells us the region in space where the electron is likely to be found 90% of the time. And so that kind of is an important parameter as well when we start drawing these pictures that are going to be used to define orbitals. So something like that, I'm just estimating it here, is the 90% probability region. And if we project that out into 3 dimensions, because here we're just showing a 2-dimensional plot for a given radius, but if we go to all 3 dimensions, for a hydrogen atom, that 90% probability region is represented by a sphere. So the ground state orbital or wave function for a hydrogen atom, if we do the radial probability distribution function and we project it in 3 dimensions, it looks like a sphere where there's going to be, I don't know what the exact radius is, but some radius where the electron is likely to be found 90% of the time. And so it just looks like a sphere. This is another projection of that where the darkness of the color, which you can see gets lighter and lighter as you move away. The darkness tells you how likely the electron is to be found there, and so on. So there's some different pictures in the book, some different ways to think about this. But for now, we just want to know that we have the difference between probability density, which is shown on the left, radial probability density, which is shown on the right, and the idea that these wave functions tell us regions in space where the electron is likely to be found, but you can never know exactly where the electron is going to be. So as we start defining more and more orbitals, we want to do this in a simpler way and be able to classify these things. And so instead of dealing with these horribly complex mathematical functions all the time that the wave functions are, we use a series of quantum numbers that allow us to define those wave functions much more simply. So we saw last time that hydrogen in the Bohr model has quantum numbers associated with those n values, 1, 2, 3, and 4. But if we're going to start defining multi-electron atoms, and if we're going to start defining orbitals that are more complicated than just the ground state of hydrogen, we need to have other quantum numbers as well that allow us to define those orbitals. And these quantum numbers will tell us different things about the orbital. They'll tell us the shape of the orbital primarily. They'll tell us in some sense the orientation of that orbital in space. In other words, gives us some idea of what these things look like pictorially. All right, so the quantum numbers, by definition, they're a series of integers. At least the first 3 that we'll deal with are integers. There's a 4th quantum number we'll get to at the very end. And these integers are all part of the wave function. So if we were to write out the wave function, it would be parameterized in some way using these integers. So the quantum numbers are parts of the wave function. And by using these quantum numbers, we can describe the energy, shape, and orientation of an orbital. So just by considering a set of 3 integers, we can know a lot of things about the orbital that we're interested in. We don't have to consider the full wave function. We don't have to draw those probability density plots every single time. We can just relate these quantum numbers to a very simple picture of the orbital that tells us the likely region in space where the electron is going to be if it's found inside of that orbital. So that's kind of what these quantum numbers tell us. So there are 3 quantum numbers that define an orbital. So if we're going to define a single orbital, we need 3 numbers. So the first one is n. This is identical to what you have in the Bohr model, and it has the same allowed values, 1, 2, 3, 4, and so on. So it's a positive integer starting with 1, and it can have any value up to infinity. And we saw in the Bohr model that value of n told us how far away from the nucleus the electron is, and it also told us the energy of the electron if it was in one of those quantum numbers. So what we call n is the principal quantum number. Or sometimes the first quantum number. And then the 2 things that it tells us are the energy and size of the orbital, or at least the relative energy and relative size. You would need the full wave functions and the full Schrodinger equation to know exactly what these values are for the energy and the size. But by using the quantum numbers, you can at least know the relative energy and the relative sizes of orbitals for a given atom. Now, when I say the size of an orbital, remember that I mean the 90% probability region, the region in space defined by that orbital where the electron is most likely to be found. It means the electron could exist anywhere within there. And then another synonym for principal quantum number is what's called the shell number. And this is likely an artifact of the Bohr model, where if you're in the, if n equals 1, that means you're in the first shell. If n equals 2, you're in the second shell and third shell and so on. So that's another way to say that. Now the second quantum number, which we haven't seen yet and is important for defining orbitals, is L, cursive L, so it looks like a little lowercase l like that. And what are the allowed values of L? So the values of L that are allowed depend on the value of n. So if you're in the first shell, you have a certain number of L values that are possible. If you're in the second shell, you have a certain number of L values that are possible. And how those are defined is that L is going to be less than or equal to n minus 1, greater than or equal to 0. Okay? So we'll see how that breaks down for different shell numbers later on. But those are the allowed values of L. And the way to think of that is it starts at 0 and goes all the way to n minus 1, including, again, only integer values. All of these first 3 quantum numbers have to be integers, whole number values. You're not going to have any fractions for these 3. Okay, so those are the allowed values of L. What does this tell us? Now, quantum mechanically, this is the angular momentum quantum number, so it's related to the angular momentum of an electron as it as it's moving around within that given orbital. So that's what it's called. We're not going to really deal with angular momentum directly when we use this quantum number. But why it's important for us is that the value of L tells us the shape of the orbital. So we saw that the hydrogen ground state is a spherical shaped orbital, but not all orbitals have a nice spherical shape. And if you know the value of L, that's going to tell you what the characteristic shape of that orbital is. The other importance of the second quantum number L is that it does contribute to the energy of the orbital. And that's true if you have more than one electron, I should say. Okay, so whenever you have an atom that has more than one electron, the energy of the orbital is determined by both n and L together. And this is a point that trips a lot of people up on homework assignments and tests, so I'll try to say it very clearly now. If you have a one-electron atom, as we talked about last time, we know from the Bohr equation that the energy level only depends on n, which is the first quantum number. If you have more than one electron, the energy level depends on n and L together. Okay, so there's a key distinction there between single electron and multi-electron species. And we know if we look at the Bohr equation, it only has n in it, it doesn't have L in it. So for one electron species, n is sufficient to define the energy. For more than one electron, you need the first 2 quantum numbers, n and L together. And then the third quantum number that's associated with an orbital is m sub L. So it's lowercase m with the subscript L. And the allowed values for m sub L are, it goes up to L and it starts at negative L. And it includes 0. So it's all the positive and negative values of L and everything in between as integer values. So what this is called quantum mechanically is this the magnetic quantum number. So it determines how strongly that orbital interacts with the magnetic field, but that's not something we have to worry about. What it tells us is the orientation of the orbital. So for a given L value, you're going to have a certain shape for that orbital, and then all the individual m sub L values are going to reflect that shape being oriented differently in space. And when we draw the pictures of these, you'll see more clearly what that means. But that's what those three things, those three quantum numbers mean for us, and they're all going to be used together to define an individual orbital. All right, so let's talk some more. One more definition that is important, which is called sublevel. And so if we want to know what kind of orbital we have, as we said, that's related to the second quantum number. That tells us the shape of the orbital. So very often what you'll see is that you'll have the first two quantum numbers paired together, n and L, and that pair tells us, or is referred to as a sublevel or subshell. Sublevel or sometimes subshell. All right, and this is important because as we talked about, the energy levels of the orbitals in the multi-electron atom are determined by n and L together. So we need to know we need to define all the different subshells and rank them in terms of their increasing energy. That's something we're going to start doing more next time. So that's why it's important to consider those two together very often. And also it tells us the shape of the orbital, because all of the orbitals that are in a given subshell have the same shape, just different orientations. And so what you have then is, based on the value of L, you use different designations for the type of orbital that you have. So L can have the values 0, 1, 2, 3, 4, and so on. Depending on the value of n that it's paired with, it can have one or more of these allowed values. And so whenever L equals 0, we call that an s orbital, or an s subshell, if we're talking about things in terms of a subshell. If L equals 1, we call those p orbitals, or a p subshell, if we're talking about a group of p orbitals all together in the same subshell. L equals 2 gives us d orbitals. L equals 3 are f orbitals. And then from there, it basically goes alphabetical. So you have S, P, D, F, and then beyond that, you'll have G and H and so on. I think it might skip J, but we're never going to go that high anyway. The only ones we really are going to see in chemistry are these four here, because these are the ones that occur in atomic ground states. In other words, all the electrons that are going to be present in an atom, no matter how big the atom is, no matter how many electrons it has, are going to be in either an S, P, D, or F subshell. You never have to go to G or H for any real atom. I think the most recent, I have to look back at this, I think the most recent element that was discovered, which is number 118, one of those ones that, as I said, lasts for a split second and is gone. I think in that case, they've completely filled up the F subshells. So I guess if they were to start making more elements, a few more beyond that might take us into G, but I don't know if they'll do that anytime soon or not. But for the ones that we're going to talk about in this class, S, P, D, and F subshells are the only ones that occur. Those are the only ones that occur in atomic ground states. So then let's see how these different allowed values of quantum numbers work, what we call the quantum number hierarchy. And so, as I said, the value of n is going to determine which values of L are possible, and then the values of L are going to determine which values of m sub L are possible. So let's see how that works. If n equals 1, that's the first value of n that's allowed. Remember that the values of L that are possible are 0 to n minus 1. I'm going to pull this out a little bit so they don't overlap. Alright, so if n equals 1, what's the value of L then? What's 1 minus 1? And then so 0 to 0, which is only 0. So if n equals 1, you can only have L equals 0. That's the only allowed value of L. And then similarly, m sub L goes to minus L all the way to plus L. And so if L equals 0, what's the value or values of m sub L? Also just 0, because negative 0 is 0 and positive 0 is 0. So those are the only values that you get. So in the first shell, n equals 1, the only allowed value of L is 0. And then for that 1s subshell, the 1, 0 subshell, the only allowed value of m sub L is 0. Now if we go to a higher shell, the second shell, n equals 2, L can be anywhere from 0 to n minus 1. So the largest value of L is going to be 1. 2 minus 1 is 1. But then it can also be 0. It starts 0 will be the smallest value. It's any integer value in between. There is no integer values in between 0 and 1. So when you have n equals 2, the allowed values of L are 0 and 1. And those are two values of L. And then for those two values of L, you have different allowed values of m sub L. So when L equals 0, as we saw before, the only allowed value of... I guess I'm drawing arrows today. The only allowed value of m sub L is 0, but then when you have L equals 1, you go from minus L to plus L, so you have 3 allowed values of m sub L. It can be minus L, which is minus 1, including 0, all the way to plus L. So you have minus 1, 0, and 1. And then we'll see if I have enough room to do this last one. So when you have n equals 3, that's the highest we're going to go for now. N equals 3, you now have 3 allowed values of L. So L goes from 0 to n minus 1. N minus 1 is 2. And then 0 is the smallest value. 1 is in between. So you have 0, 1, and 2. All the integer values between 0 and 2. And then if we go from these different L values that are allowed, again, if L equals 0, we already saw that m sub L has to be 0. If L equals 1, the only allowed values of m sub L are minus 1, 0, and 1. That's exactly the same we saw last time. Then we have this n equals 2 here, and there's going to be 5 allowed values, which I'm running out of room here. We're going to have all the way from minus L to plus L. So if L equals 2, you go from 2 to minus 2, and then every value in between, minus 1, 0, and 1. So minus 2, minus 1, 0, 1, and 2. So that's sort of the types of things we're going to see a lot in homework problems. We'll tell you, if the value of n is 3, what are the allowed values of L? And you have to say, well, 0, 1, 2. Or if the value of L is 2, what are the allowed values of m sub L? So knowing these relationships between the quantum numbers is sort of the first step going towards understanding them. So that's what we refer to as the hierarchy of quantum numbers, where the allowed value depends on all the previous values. So let's talk about a couple example problems, and then we'll see some shortcuts as well that might help us in some of these. So let's say we have the third shell, n equals 3. We want to know how many orbitals are in the third shell. So what we have to keep in mind is that if we're defining an individual orbital, we want to count up how many individual orbitals are there in a shell. We have to remember that an orbital is defined by 3 quantum numbers. N, L, and m sub L. So in other words, within the third shell, every allowed set of n, L, and m sub L quantum numbers is going to define a single orbital. I want to know how many of those combinations are possible using the rules for quantum numbers. So what we could do is we could do it kind of like we did here. This would be the long way of doing it. We could say, okay, n equals 3, L has these values. How many possible combinations of those are there? So there's 3, 0, 0, 3, 1, minus 1, 3, 1, 0, 3, 1, 1, 3, 2, minus 2, 3, 2, minus 1, 3, 2, 0, 3, 2, 1, 3, 2, 2. Count up, or in other words, we just have to count up all of the allowed m sub l values, or how many of them there are. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 m sub l values at the bottom of this hierarchy, which means that there are 9 orbitals. Now this is a long way to do it because even for n equals 3, you had to write out 9 combinations and make sure you didn't forget any. If you go to n equals 4 or 5, the numbers go up and up from there. So a shortcut that we can use, and we just have to make sure we remember these correctly to be able to use them properly. If you're given a value of n, we want to know how many orbitals are in that shell, which is what this question is asking us. The number of orbitals is given by n squared. Okay? So for whatever value of n you're considering, 0, 1, or sorry, not 0, 1, 2, 3, 4, 5, and so on, even if you're considering hypothetical values of n that don't even occur in real atoms, you could predict how many orbitals are in that shell just by squaring the value of n. Now if we're giving you a subshell, so if we give you an n and an l together, and instead we were asking how many orbitals are in this subshell, it's a little bit different. So in a subshell, you're given a value of n and l, and the number of orbitals in that subshell is going to be determined by the l value, and it's going to be 2l plus 1. Okay? So you have to keep in mind when we're asking these questions, whether we're talking about a shell or a subshell, if you're trying to figure out how many orbitals are in that shell or subshell and which of these relationships to use. So for this problem, if we're talking about the third shell, a shell is defined only by a value of n, and so for that we just take 3 squared is 9 orbitals. Same number we got by counting up all the individual allowed sets of n, l, and m sub l that we wrote out on the last page. Okay, so you get 9 orbitals in the third shell. If we wanted to instead do, let's just do another random example that's not written here. Let's just say we wanted to figure out how many of these orbitals are in the 3D subshell. So if we're given a subshell designation, we have a value of n and l, and the number of orbitals in that subshell is determined by the value of l. So for a 3D subshell, l equals 2. Remember we have that S, P, D, F. S is L equals 0, P is L equals 1, D is L equals 2. We wrote that a couple slides ago. And so if L equals 2, we have the number of orbitals in the 3D subshell is 2L plus 1. 2 times 2 plus 1, which is 5. So these are shortcuts you can use instead of writing out all of the possible combinations of n, l, and m sub l that work for that given shell or subshell, because those sometimes take a while. This gives you those answers a lot quicker if you just want to know the number of orbitals in that shell or subshell. So if we look at this result here that we got, in the third shell there are 9 total orbitals, and 5 of those 9 orbitals are in the 3D subshell. The other 4 would be in the 2 other subshells that are present, the 3s and the 3p. Okay, so these are some of the relationships between quantum numbers. Let's do one more that's very closely related to this. How many f orbitals are present in a given f sublevel? Okay, so whenever we're given a subshell, which is defined by a value of n and l, it turns out we don't need the value of n if we're just trying to find the number of f orbitals that are in a sublevel. So we just need to find the value of l because this is a sublevel, and then that letter f tells us what the value of l is. So the allowed values of L are 0, 1, 2, 3, and so on. And these correspond to the letter designations S, P, D, and F. You'll have to, burn that into your memory very quickly. So when we have an F subshell or an F sublevel, L equals 3. And the number of orbitals is given by 2L plus 1. Which is 7. So for any F subshell, whether it's 4F, 5F, 6F, whatever, the value of L, 3 tells us there's going to be 7 orbitals in that subshell. Okay, so by knowing the different quantum numbers, we can predict then how many orbitals there are, and as we'll see later, that's related then to how many total electrons we can put in that subshell, which is another important thing we'll talk about next time. All right, so moving on, we've talked about these quantum numbers. Let's see how they then relate to the shape of the atomic orbital. All right, so we want to draw pictures, which are a lot more satisfying for us, and we'll use these pictures quite a bit when we're talking about, especially when we start talking about bonding, the ability of these atoms to overlap and form bonds. We want to know the shapes of the orbitals, the regions in space where the electrons can exist, because that's also related to how those atoms can form bonds with each other, so these are going to be important for a while. So first we need some terminology to tell us some things about the shapes of orbitals. The first is node. So the node is a region where the electron has zero probability of existing. I didn't spell that right. Alright, so a node is a region where there's zero probability of finding the electron. And there are two types of nodes that we're going to consider when we're talking about the shapes of orbitals. The first one, which is not terribly important for just defining the basic shape of the orbital, but it's something we want to think about in other contexts, is what's called a radial node. So a radial node is a certain radius defined by r relative to the nucleus, always, as we're talking about in these cases. And a radial node is a certain radius where the probability of finding an electron is zero. We didn't see that in the one we've talked about already, the ground state of hydrogen, but for other types of orbitals, we do have the possibility of having radial nodes. Now another way to think about nodes, both the two types of nodes we're going to talk about, is it's a place where the wave function goes to zero. So the wave function is a mathematical function that's going to have certain values as a function of r or as a function of x, y, and z, depending on how you parameterize the function. And there are going to be certain places where the wave function has a value that's exactly equal to zero, and that's where the nodes are going to be located. So you have a radial node, which is a radius at which the electron cannot exist, some distance from the nucleus. And you can very easily predict the number of radial nodes by knowing the quantum numbers that are associated with that orbital. So it's going to be n minus L minus 1. Okay, so each orbital is going to have a characteristic value of n and L, as well as m sub L, but the number of radial nodes is determined by the values of n and L. N minus L minus 1 tells you how many radial nodes there are. And then the other type of node is the nodal plane, because something that isn't terribly important for the hydrogen wave function because it's spherical, but is an important factor for other types of orbitals, is that they have both a radial and an angular component. So the radial component, again, is a description of probability as a function of distance from the nucleus, and then the angular component gives you the distinct shapes of all the orbitals. If you've ever worked in polar coordinates, you might be familiar with the idea of dividing up a function into radial and angular components. We do the same thing for wave functions. And so a nodal plane is related to the angular component of the wave function, and it's a two-dimensional plane where the electron has no probability of existing. In one case, we'll see that the nodal plane is actually more like a nodal cone, but it's still just a flat region in space, or a two-dimensional region in space where the electron can't exist. And the number of nodal planes is very easy to know. It's just the value of L. Okay. So we said that L determines the shape of the orbital. The shape of the orbital is determined by how many nodal planes it has, as we'll see when we start drawing these. Okay? Okay, questions on this so far? Okay, let's move on then to start drawing the shapes of these orbitals. We'll start with the relatively simple ones, the s orbitals. So s orbitals means L equals 0. And all of the s orbitals are going to be spherical in shape. And because L equals 0, they have 0 nodal planes, and that's why they're spheres. Now, the only thing that's going to differ between the different s orbitals, whether you're talking about 1s, 2s, or 3s, is going to be the number of radial nodes then. So if you have a 1s orbital, the number of radial nodes is given by n minus L minus 1. So n is 1. L is 0, minus 1 equals 0. So a 1s orbital will have 0 radial nodes, and this is basically the hydrogen ground state wave function, or looks identical to that. So the radial probability density for a 1s orbital is going to look exactly like we drew before. It has a peak somewhere, and then it approaches but never goes to 0 the farther away you get from the nucleus. Okay? So a 1s orbital has no radial nodes, so it has this very simple probability density. If we go to a 2s orbital, though, where n equals 2, L still equals 0, n minus L minus 1 is going to be 2 minus 0 minus 1. So you're going to have 1 radial node. And so how does this change the shape of the radial probability density? What it means is that you're going to have some radius away from the nucleus where the probability goes to 0. So you're going to have a little peak there, and then another larger one farther away. Okay, so it's going to look something like this. If we try to draw this in three-dimensional space, what does it look like? It's still a sphere, but then, so the total probability density, the 90% probability density, is going to be encompassed in a sphere of some radius. But there's going to be some radius within there where the electron cannot exist. So it would basically look like two concentric spheres. A smaller sphere on the inside that corresponds to this region, and then a larger sphere that corresponds to that region. Still, the overall shape is spherical for any s orbital. Now, the question that's boggled my mind for years since I took chemistry, and maybe I shouldn't say, was it 2003, 2004 that I took this class? And the question that's been burning a hole in my brain since then is, okay, so you have this, region of non-zero probability close to the nucleus. You have a region of non-zero probability a little bit farther away. How does it get from one place to the other, without crossing through a region where there's zero probability? In other words, how do these nodes work? How can the electron get from here to here if it has to go through a radius that has zero probability? And that's what's called tunneling. It's not a big mystery, but it's one of those, quantum mechanical things that'll drive you nuts the more you think about it. So the idea that you have a region at some radius where the probability is zero, but somehow the electron can exist on either side of that radius, either closer to or further away from the nucleus, it just drives you crazy thinking about it. So my suggestion is not to think about it too much. But anyway, that's what we mean by a radial node. So that's how the radial probability density changes. And then the last one we'll do is 3s. N equals 3 now, L still equals 0 for any s orbital, and you have 2 radial nodes. And so when you have 2 radial nodes, you get sort of 2 little peaks before you get your sort of... Now, the other thing that I've tried to depict, and will become important more later on as we do this, it's maybe not terribly accurate for my documents, but if you look at the most probable radius in these, it is shifting further and further away from the nucleus. The value of r that is most probable, that top peak there, as we call it, that's getting further and further away from the nucleus. And that is true. That's another effect of changing the value of n. So as you go from n equals 1 to n equals 2 to n equals 3, you would say that the orbital gets bigger. The region where the electron is most likely to be found gets bigger and bigger and bigger, gets larger and larger radius as the value of n gets larger. So that's another thing to take out of these pictures here, which is important when we start ranking the order of these orbitals in terms of their energies. We'll talk about next time. So those are the shapes of the s orbitals. Those are the simple ones. Now let's move on to the p orbitals. We'll do the 2p orbitals. 3p would be the same, just with more radial nodes, similar to what we saw. So if we have the p orbitals, what do we have going on here? If we wanted to draw the radial probability density for a 2p orbital, we're not going to talk about radial probabilities too much for p orbitals, but if we wanted to, n equals 2 and L equals 1 now. So the difference between a 2p orbital and a 2s orbital is that L equals 1 instead of 0. And if we have these two values of n and L, we're going to still have 0 radial nodes. N minus L minus 1 is still 0. So the radial probability distribution for a 2p orbital would look a lot like a 1s orbital, just a single peak, no radial nodes. The big difference, though, is now we have one nodal plane, because the number of nodal planes is equivalent to the value of L. So we have a nodal plane, which tells us that the shape of the orbital is going to be different. So mathematically, that means the radial part of the wave function for a 2p orbital is distinct from the angular part of the wave function is distinct from that of an s orbital. And so we have one nodal plane which changes the shape of the orbital. So when you have a nodal plane, the way the orbital shape changes is that instead of becoming a sphere, it looks more like a dumbbell or a figure 8, I guess, but three-dimensional. The other thing that's important is because L equals 1, we have three values of m sub L, minus 1, 0, and plus 1, which means we're going to have three individual 2p orbitals that differ with respect to their orientation in space. Okay? So one of those we'll call the px orbital, and so as the name implies, it's oriented along the x-axis. It's a figure 8, but sort of three-dimensional, so we'll call these dumbbell-shaped. And so we're aligned along the x-axis like that. And the nodal plane then, which cuts this in half, so imagine cutting that orbital in half, is going to be this plane here defined by the y and z axes. So if you have a px orbital, the other two Cartesian coordinates define the plane that is the nodal plane for that. So this has a yz nodal plane. Now when you look at the pictures in your book, they're kind of shown like this. It's just a simple dumbbell shape where the two lobes have the same color. What I like to draw, and what's going to be important later on when we talk about bonding, is the idea that really you have two different phases of your orbital. And so what that means is you often see these drawn with one of the lobes shaded like that. What that tells you is that the wave function has two different signs as you go through the nodal plane. So the other consequence of a nodal plane is not only is the probability 0 there, but as you cross over the nodal plane, the sign of the wave function changes, and that's going to be important when we talk about bonding later on. It's not so important for us now. But the shape is a figure 8, but you have two different phases or two different signs of the wave function on each side of that. That's why we often draw them with two different colors. If you have the px orbital, the other two are just oriented along the other axes. So you have the py, which is along the y-axis. And again, one of those lobes is going to be shaded. And if the orbital is along the y-axis, that means the nodal plane is the plane that's perpendicular to y, which is going to be xz. And then the last one is going to be along the z-axis, pz. So vertical as I've drawn it here, where you're going to still have one shaded lobe, and the perpendicular plane, which is xy, is going to be your nodal plane. Okay, so these are the three individual 2p orbitals, which only differ with respect to their orientation in space. They're all dumbbell shaped. They all have one positive phase, one negative phase. Which one you define as positive and negative is arbitrary. They're just two different phases, but they're just going to be oriented differently with respect to the x, y, and z axes. Okay, so those are the p orbitals. A big limitation of Blackboard is that we can't ask you guys to draw pictures. So you wouldn't have to draw these yourselves, but you do need to be able to recognize them. If we gave you a picture of one of these orbitals, you'd be able to tell us, is it a px, py, or pz orbital, or some other type of orbital. The last type of orbital you're going to be responsible for knowing are the d orbitals. Okay? So we'll do 3d, n equals 3, L equals 2. just like before, these 3D orbitals have 0 radial nodes, so the radial probability distribution is going to look the same. And then you're going to have this same basic shape here for the radial probability distribution. That doesn't tell us anything, but because L equals 2, we have 2 nodal planes, and so the shape of the d orbitals is different. Okay. So there's going to be 5 d orbitals because we have 5 allowed values of m sub L now. -2, -1, 0, 1, and 2. There's not a direct correlation between which m sub L value corresponds to which orbital, but the fact of the matter is there are going to be 5 orbitals because we have 5 allowed m sub L values. And so most of the d orbitals, 4 of the 5 d orbitals are just shaped like 4-leaf clovers. And they're just, again, arranged differently in space to distinguish them from each other. So there's 3 that are labeled with 2 Cartesian coordinates. So you have xy is one of them. And so when you have the dxy orbital, what that means is that you have 4 lobes, and the 4 lobes lie in between the x and the y axes. So you have one that goes like that, in between those 2 axes in that direction, a lobe like that, and like that. So this is in the xy plane, with the lobes in between the x and the y axes in a sort of 4-leaf clover arrangement. And the ones that are opposite each other have the same phase. So you get sort of this alternating, shaded, unshaded, representing the alternating phases of the orbital. If we talk about the nodal planes here, you would have a nodal plane that's in the xz plane, or sort of like this, and then another nodal plane that's kind of in the yz direction that cuts that orbital in half in 2 directions. So we're not going to worry too much about the nodal planes for these, but there are 2 of them that cut the orbital in half in either direction every time we change phase that involves a nodal plane, as we talked about. So that's the dxy orbital. There's 2 others that are the same exact thing, but just in a different direction. So dyz has the same shape, but is in the yz plane. So you have, in this case, I'll highlight those axes. You have the y and the z axes that are defining that d orbital, and so the orbital is going to be oriented along those for the dyz. Okay, and then finally the last one that looks very similar to that is dxz. So for the dxz orbital, we're going to be, as the name implies, along the x and z axes. So I'm highlighting those as the axes that the orbital is oriented along, and you have your 4 lobes that go in between the x and the z. The last one that looks like a 4-leaf clover, and perhaps the simplest one to draw in the picture, is the dx squared minus y squared. And this one is basically it's the dxy, but it's just rotated 45 degrees such that the lobes are right on the axis. So we have one lobe right along the x-axis, another lobe in the opposite x direction, and then one lobe along y, and another one along y. Alright, so it's exactly the same as dxy. It's in the xy plane, but it's just rotated 45 degrees such that the lobes are right along the axis. So these 4 all look the same, they just have different orientations. The last one that's sort of the oddball is dz squared. So dz squared is aligned along the z-axis. The name kind of tells you that. It looks kind of like a p orbital at the beginning. It's just that the 2 phases are the same instead of different. But then it has this torus, or what I like to call the donut, that goes around the middle of it. Alright, so imagine putting a dumbbell through a hollow ring, and that's what your dz squared looks like. You're threading it through. So those are the 2 different phases. The 2 lobes are one phase, and then the torus or the donut is the second phase. This is the one that I mentioned has a nodal cone that goes out in both directions, not really a nodal plane. But it's just a different shape. You want to recognize that as being the dz squared orbital. So those are the drawings, and you just have to become familiar with those, recognizing that most of the d orbitals have the same shape, just oriented differently in space, and the name tells you the orientation, x, y, x, z, and so on. Now, because it's difficult to draw in 3 dimensions, especially for someone like myself who flunked kindergarten for poor motor skills, which is a true story, I reproduced the pictures from your book here in case you don't have the book. These might be a little bit easier to interpret, showing the three-dimensional shapes. As I said, these pictures from the book do not show you the relative phase of the orbitals. They're all given in one solid color, so keep in mind that that information is left out. But maybe it more clearly shows the orientation of these orbitals in 3 dimensions where they're able to use creative shading and things to do that. So that's what the d orbitals look like. We're not going to do f orbitals because I couldn't even draw those if I tried. Now let's just do a couple sample problems about orbitals before we wrap this section up. So we have, which of the following orbital designations is incorrect? So we want to know, in other words, which of these is not an allowed value for a set of 3 quantum numbers? So, or sorry, I guess there are only 2 quantum numbers here. So n equals 2, L equals 0 is 2s. Is that correct? So if n equals 2, the values of L are 0 and 1. And if L equals 0, that would be an s orbital. So that one's okay. If n equals 3 for choice B, the allowed values of L are 0, 1, and 2. So L equals 1 is okay. If L equals 1, that's a p orbital. So this one is correct. For choice C, n equals 4. The allowed values of L are going to be 0, 1, 2, and 3. If L equals 2, that's going to be a d orbital. So 4d is correct. And then finally, by process of elimination, the last one should be the one that's incorrect. So n equals 3. The allowed values of L are going to be 0, 1, and 2. So you cannot have an L equals 3 if n also equals 3. So there's no such thing as a 3f orbital because when n equals 3, the maximum value of L is 2, which would be d. So this is not an allowed value, and so that one's going to be the one that's incorrect, or I guess I should circle it because that's the correct answer for this question. Okay, so again, just getting used to the relationships between quantum numbers and how those translate into orbital labels. And then finally, what's the name of this orbital pictured at right? So it looks a little bit different than the one that I gave you. Now, the first thing we should keep in mind is the overall basic shape of the orbital has 4 lobes. So what kind of orbital is that automatically? It's a d orbital. So it can't be a p orbital. So we can get rid of that one. It's along the x and the y axes, so it can't be the dz squared because dz squared is along z. So then finally we have to remember the difference between x squared minus y squared and xy. The xy orbital would have its lobes in between the x and y axes. These ones, the lobes are right on the axis, so it's going to be dx squared minus y squared. Okay? So just get used to recognizing those. And then finally, the last thing I want to talk about, there's one slide left, we're almost done, is the 4th quantum number. So we've now used 3 quantum numbers, n, L, and m sub L to define orbitals, but there is a 4th quantum number we have to worry about when we start putting electrons into these orbitals. And that last quantum number is called the spin quantum number. And it only has 2 possible values, and they don't depend on the values of n and L and m sub L, so it's independent of those. And the only 2 values are plus 1/2 and minus 1/2, so plus and minus 1/2. Okay, 2 values for m sub s. And the terminology that we use to describe those, if m sub s is plus 1/2, we say that that's an electron that is spin up. And then if m sub s is minus 1/2, we say that's an electron that's spin down. So that's just kind of the terminology that you'll hear a lot in chemistry describing the 2 different m sub s values, plus 1/2, minus 1/2. Alright, so it only has 2 values, and unlike the other 3 quantum numbers which depend on each other and which define an orbital, m sub s is a property of the electron itself. And is related to the direction of the electron's magnetic field. So we know from physics that a charged particle that's moving is going to generate a magnetic field, and the direction of that magnetic field for an electron is defined by the m sub s value. Again, that's the physical definition that we're not going to really use too much in chemistry, but that's sort of what it derives from quantum mechanically. And so finally, that gives us the set of 4 quantum numbers that we're going to need to define any electron in an atom. So any electron in an atom is going to have an n, an l, and an m sub l value. Those are going to tell us what orbital it's in. But then each individual electron is also going to have an m sub s value that tells you whether it's spin up or spin down. And so when we come back next time, we're going to start talking about how to define the 4 quantum numbers for any electron in an atom and how we start populating the orbitals with electrons and ordering them in terms of their energy and everything like that. All right, so I'll see you guys on Monday. As a reminder, office hours are cut short tomorrow. I'll be leaving at 12:30 and not available for the rest of the week after that.